Hi, I'm Pranaya and I'm here to present Regularized Latent Dynamics Prediction, which is a simple representation learning method for behavioral foundation models. Say you get a robot delivered in a box. You want the robot to be able to do a wide range of tasks without having to train the agent each time for a new task. Our work takes a step towards this motivation. The goal of reinforcement learning is reward maximization. To train RL agents to perform specific tasks typically requires reward design. For example, say you want to train a humanoid agent with RL to water plants. This will usually require an expert engineer with domain knowledge to design reward functions that can capture the complexity of the task. This makes reward design inaccessible to people unfamiliar with domain knowledge. Also, what we truly want are generalist agents. As more and more people interact with these agents, we want the agents to be able to perform a wide variety of tasks. Reward design can rapidly become infeasible when we want the agent to learn to perform several different tasks, and has the risk of reward hacking. The challenge is to build a reusable behavioral backbone that can support a broad family of downstream objectives. This is where unsupervised RL comes in. It has a pre-training phase and an inference phase. In the pre-training phase, we take reward-free transitions and we define a set of reward functions that are in the linear span of learned state features. This means our reward function is a dot product of features and a latent vector z. For each such z-defining reward function, we learn a z-conditioned policy that optimizes the associated reward function. We call the z-latent space as the skill space of the agent. At test time, we are able to find task embedding z by minimizing the mean squared error to the test reward function, which can be solved in closed form. This gives us a z-conditioned near-optimal policy. This pre-trained decision-making model is Behavioral Foundation Model, or BFM, and it is trained in an entirely unsupervised way with reward-free transition data and can produce approximately optimal policies for a large class of reward functions at test time without additional learning or planning. Learned representations are central to unsupervised RL since we pre-train the representations and adapt them to many tasks at inference. In other words, the representations are the interface between reward specification and behavior, and they determine the skills that the agent is able to learn. So, the agent needs features that can capture the right distinctions in the environment. Bad representations can lead to agents lacking skills or representation collapse, which at best may be unhelpful or at worst even lead to harmful behavior. Many prior methods often learn representations with Bellman-style bootstrapping, typically by modeling successor measures. This is a powerful objective, but it is also complex and it can suffer when the policy collecting the data has low coverage. With this work, we question if we can replace this with something simpler, just predicting the next latent state. We find that using naive latent next state prediction can cause a mild form of collapse, where the representations of different states become increasingly similar over training. This is especially problematic in zero-shot RL because the span of possible downstream rewards for which we can find an optimal policy is determined by these same features. We find that using a simple fix, keeping the latent prediction objective but adding orthogonality regularization to encourage feature diversity can give us more diverse representations. This gives us RLDP, Regularized Latent Dynamics Prediction, where the goal is to make the features both predictive of future state evolution and diverse enough to support a broad family of rewards. Overall, our representation learning approach comes together like this. We begin with reward-free transitions. The primary representation learning objective is unrolled latent dynamics prediction. We learn a state representation encoder and a dynamics model such that the dynamics model can predict future latent states given current latent state and action. We add diversity regularization of the latent states to ensure representation diversity. After representation learning, we freeze the encoder and train the behavioral foundation model as described before. To evaluate our method quantitatively, we begin by examining whether RLDP can learn representations competitive to existing baselines. On offline zero-shot RL benchmarks, RLDP is competitive with strong baselines like forward-backward and proto-successor measure. Next, we ask if learned representations enable competitive multitask learning when the agent is allowed interaction with the environment. For this experiment, we use high-dimensional SMPL humanoid environment. The violent plot having mean above 0 indicates that RLDP is mostly competitive and sometimes better than baseline representation learning methods, but the performance varies by task. RLDP learns policy-independent representations through latent dynamics prediction. However, many prior approaches assume a class of policies to learn representations predictive of successor measures, and this strategy can lead to poor out-of-distribution generalization when the actions approached by the policy are not covered by the dataset. Finally, to evaluate this hypothesis concretely, we consider the D4RL benchmark of OpenAI Jimujoko tasks. The violent plot shows one-to-one comparison of normalized returns of RLDP against baseline methods. the overall mass of the violin lies above 0, indicating that RLDP outperforms baseline methods in many of these tasks. Concretely, numbers indicate that RLDP is better on 5 out of 6 tasks. More detailed results are available in the paper. RLDP learns predictive latent representations. So, a natural next step is to wonder if these same latents can support multi-step prediction, imagination, and planning. We already show it can work in complex high-dimensional humanoid as well as under low coverage setting. RLDP is demonstrably simple, scalable, and robust. Since this method works in the latent space, it could also be a useful foundation for world modeling. Please visit our poster or our paper to find out more.